International FDP program conducted by Department of Mathematics under the title of Exploring Innovations in Mathematics and Statistics. Today, we are presenting qualitative analysis of fractional delay differential equations with delayed perturbation of matrices by Dr. T. Satyaraj. I now request Mr. S. Loganathan, Assistant Professor of Department of Maths, to introduce the research person for the day.
Thank you, ma'am. Good evening to all. On behalf of Department of Mathematics, School of Arts and Science, I am going to introduce today's resource person, Dr. T. Satyaraj, Postdoctoral Research Fellow, Department of Mathematics, Zog University, China. He completed his PhD in Gandhigram Rural Institute, deemed to be University, Tamil Nadu in 2017. He received Senior Research Fellow Award by CSIR, New Delhi. He published many papers in reputed international journals. He is also a member in the editorial board to review the journal paper. His native place is Tanjavur. Thank you. I welcome you, sir. Thank you, ma'am.
Thank you, sir.
Thank you, sir. Thank you.
With that, we'll turn the time over to Dr. T. Satyaraj. Sir, please take over the session, sir.
Thank you, ma'am. Thank you. Ma'am, my slide is visible?
Sir, there is a background
Yes, sir. Yes, sir.
over it.
Pardon, sir?
There is background noise.
Some background noise is there, sir.
Some noises?
Yes, sir.
Oh, wait a moment.
Song is
Okay, is it better now, ma'am?
Yes, sir. Yes, sir.
So first of all, I thank all the participants and the management to giving me the opportunity to deliver the lecturer in the FDP program. So in this regard, I wish to present my present entitled with the qualitative analysis of fractional delayed differential equations with the delayed perturbation of matrices. I hope the presentation will be useful for all the participants, those who are studying and doing research in fractional differential equations. And the main objective and objective of this presentations, the participants will get basic ideas and innovative knowledge about fractional delay differential equations with the perturbation of linear matrices. Okay. The integer order differential operator d by dx d squared by dx squared, and so on, d power n by dx power n, etc., are initially invented by Leibniz. Suppose we consider the function y equal to x power m. We take n derivative for the function y equal to x power m, then we can generalize the nth derivative of the function by using gamma function, generalized gamma function. See, the first derivative of the function y equal to x power m is dy by dx, which is equal to m into x power m minus 1. The second derivative is m into m minus 1 into x power m minus 2, and so on. The nth derivative of the function y equal to x power m is d power n y divided by dx power m, which is equal to m into m minus 1, m minus 2, m minus 3, and so on, m minus n plus 1 into x power m minus n. This nth derivative we can generalize, we can write in the general form of gamma function, that is d power n y divided by dx power n, which is equal to gamma of m plus 1 divided by gamma of m minus n plus 1 into x power m minus n. Here m is an integer, but in this general notation, the number n allows to take as a fraction number, that is n equal to 1 by 2, 1 by 3, 3 by 4, like etc. So gamma function is the keynote of fractional differential equations, which plays an important role and a key role to find the fractional derivative for various functions. So the birth of fractional differential equation is developed by questions. L'Hopital asked a question to Leibniz: what if the order will be n equal to 1 by 2? Then Leibniz replied to L'Hopital, it will lead a paradox from which one day useful consequences will be drawn. So this theory, this fractional differential equation developed by questions. Now, I give some fractional derivative for the simple function. For example, y equal to x power 1 by 2. That is the half derivative of the function y equal to x power 1 by 2. Now, differentiate d power 1 by 2 y divided by dx power 1 by 2, which is equal to 1 by 2. Now, we apply the generalized gamma function. That is d power n y by dx power n, which is equal to gamma of m plus 1 divided by gamma of m minus n plus 1 into x power m minus n. We put n is equal to 1 by 2 because the derivative n equal to half. So d power 1 by 2 y by dx power 1 by 2, which is equal to gamma of m plus 1 divided by gamma of m minus 1 by 2 plus 1 into x power 1 by 2 m minus 1 by 2. Here I choose m is any integer. I take m equal to 1. Therefore, we get gamma of 2 divided by gamma of 1 by 2 plus 1 x power 1 by 4. By using gamma property, gamma 2 can be written as 1 into gamma of 1. That is gamma of n equal to n into gamma of n. By using that property, we can write 1 into gamma of 1 divided by 1 by 2 gamma of 1 by 2 into x power 1 by 4. Again, we apply the gamma function property. Gamma of 1 by 2 is equal to square root of 5. Therefore, also we know that gamma of 1 is equal to 1. Therefore, 1 into 1 equal to 1 divided by 1 by 2 into square root of gamma into x power 1 by 2. Therefore, finally we get 2 divided by square root of x power 1 by 2, which is the half derivative for the function of y equal to x power 1 by 2. Now, I give the another function, that is y equal to x. That is x power 1. Here m equal to 1. Now, again we take the half derivative for the function y equal to x, apply the generalized gamma function, gamma of m plus 1 divided by gamma of m minus n plus 1 into x power m minus 1. So again we get 1 into gamma of 1, that is m is equal to 1. So gamma of 2 can be written as 1 into gamma of 1 divided by 1 by 2 into gamma of 1 by 2 x power 1 by 4. So we get 1 divided by 1 by 2 into square root of pi x power 1 by 2, we get 2 divided by root pi into square root of x, which is equal to square root of 4x divided by pi. Now, we take the half derivative for the function y equal to 1, that is constant function. Now, we take the half derivative for the function y equal to 1. We get 2 by square root of pi. Usually, we know that the derivative of the constant function, the integer order derivative of the constant function is 0. But the fractional derivative of the constant 1 is 2 divided by square root of pi. But we know that fractional differential equation is the generalization of integer order differential equation. I'm already proved in the previous slide. That is, for the function, the half y equal to x power m, we generalize the nth derivative of the function by using gamma function. Gamma function allows n take a fractional number. Therefore, fractional differential equation is the generalization of integer order differential equation. But the derivative of the constant function is 0 in integer order. But the derivative of the constant is not equal to 0 in fractional order. For this issue, Caputo, I will explain later. Caputo gives the new formula for fractional differential equation called Caputo fractional differential equations. In that equations, the derivative of the constant function is 0. Now I consider two systems. The first one is integer order system. The same system I consider in the fractional order with the initial condition x of 0 is equal to 1 for gamma lies between open interval 0, 1. Consider the integer order differential equation. D divided by dt into x of t equal to gamma into t power gamma minus 1. The corresponding fractional differential equation is Caputo derivative of x of t, which is equal to gamma into d power gamma minus 1, where the fractional derivative alpha lies between 0 to 1. Alpha is any number which lies between 0 to 1, like 1 by 2, 1 by 3, 1 by 4, like this. So now we write the solution for integer order differential equations, also fractional order differential equations. The analytical solution of the integer order differential equations 1 can be written in the following form. That is x of t minus x of 0, which is equal to gamma into d power gamma minus 1 plus 1 divided by gamma. We can get t power gamma. That is x of t equal to x naught plus t power gamma. We know that the initial conditions x of 0 is equal to 1. Therefore, we get x of t equal to 1 plus t power gamma. Whenever t tends to infinity, the solution x of t tends to 0. That is, the solution of the integer order differential equation is unstable for gamma belongs to 0 to 1. In the real world application, in the real world applications, there is no use for unstable system. The stable system only provides some useful and meaningful applications in the real life model. The integer order system, the solution of the integer order system tends to infinity as t tends to infinity. Whenever t approaches to infinity, the time t approaches to infinity, the solution of the system tends to infinity. So obviously the system is unstable. The corresponding solution of the fractional differential equation 2 is x of t equal to 1 plus gamma plus 1 divided by gamma plus alpha t power gamma plus alpha minus 1. We write this solution by using gamma function. Whenever t approaches to infinity, the solution x of t tends to 1. That is, the system is stable, where gamma plus alpha minus 1 less than 0. Therefore, the integer order system, the non-integer order, that is the fractional order system is stable for 0 less than alpha less than or equal to 1 minus alpha. In this case, we consider two systems. One is integer order, another one is the same system corresponding to fractional order differential equations. So the integer order system provides the solution of the integer order system provide unstable whenever t approaches to infinity, but the fractional differential equation is the solution of the fractional differential equation is stable whenever t approaches to infinity. So fractional differential in particularly fractional differential equations give better results those of integer order differential equations. This is the best example for that. So this implies the fractional order system may have additional attractive features over the integer order system. Now I wish to give some basic definition for fractional order, fractional integral order, integral and fractional derivative. First we consider fractional integral of order p. Here the order p lies between not only 0 to 1, which also lies between n minus 1 strictly less than p less than or equal to n, less than or equal to n, where n belongs to set of all natural number. Which one is the generalized fractional integral order? So the fractional integral of order p with the lower limit a for the function f from closed interval a to open interval infinity to r. That is the initial time. We denote the initial point a up to infinity, which is denoted by I power p suffix a plus f of t, which is equal to 1 by gamma of p integral a to t f of s divided by t minus s power 1 minus p into ts, where t greater than a and the fractional order p is positive, because for this definition we choose p belongs to open interval n minus 1 closed interval n, where n belongs to set of all natural number, provided the right side of the right side is pointwise defined on the interval a comma infinity, where gamma is the gamma function. We know that the gamma function. So initially, RL, Riemann-Leibovitz initially introduced the fractional integral order for the function f, which is equal to 1 by gamma of q integral 0 to t minus s power q minus 1 f of s into ds. Here I power q suffix t denote the integral function with the order q at the time t. Also, he introduced the Laplace transform for Riemann-Leibovitz fractional integral, which is given by L. Here L denote the Laplace transform. The Laplace transform of Riemann fractional integral is I power q f of t is equal to 1 by lambda power q f cap of lambda. Here 1 by lambda power q is the Laplace transform of 1 by gamma of q, and f cap of lambda is the Laplace transform of the function integral 0 to t minus s power q minus 1 f of s into ds. Also I have mentioned here f cap of lambda, which is equal to integral 0 to infinity e power minus lambda t f of t dt, which is the Laplace transform of the function f of s. The definition for Riemann-Leibovitz fractional derivative for the order of the order q belongs to open interval 0 to 1 for the function f is defined by d power q t f of t, which is equal to 1 by gamma of 1 minus q t by dt into 0 to t minus s power minus q f of s ds. This RL fractional derivative can be written in terms of integral order. We know that integral order I power q f of t equal to 1 by gamma of q 0 to integral 0 to t minus s power q minus 1 f of s into ds. The only change is in the fractional derivative 1 by gamma of q is 1 by 1 minus q, and t power t minus s power q minus 1 is t minus s power p minus 1. Therefore, the fractional derivative of the RL function can be written in the form of fractional integral order. For the RL derivative, the RL derivative of the constant is not equal to 0. For that reason, the Caputo rewrite the RL derivative. In his definition, the derivative of the constant function, that is the Caputo derivative of the constant function is 0. So now, which is more popularity and more useful in many real life models. So the Caputo fractional derivative for the function q, where q belongs to open interval n minus 1, closed interval n, where n belongs to set of all natural numbers, for the function f is defined by d power q t f of t equal to 1 by gamma of n minus q, integral 0 to t f power n of s t minus s power q minus n plus 1 into ds, where f power n is the derivative. Suppose we consider the function up to higher order, like q belongs to open interval 0, 1. Suppose we choose the another derivative, p belongs to closed interval 1, open interval 2. We can choose higher order also. Whenever we choose the higher order, the derivative will be increased. I will give the detailed explanation. The Caputo fractional derivative for the function can be defined in terms of RL fractional derivative. We know that RL fractional derivative, that is d power q, which is equal to 1 by gamma of q, integral 0 to t minus s power q minus 1 f of s into ds. So the Caputo fractional derivative can be expressed in terms of RL fractional derivative. That is, the Caputo derivative of the function f of t equal to RL derivative of f of t minus f of 0, where f of 0 is the initial function or initial conditions. And its Laplace transform of the Caputo fractional derivative is Laplace transform of t power q t f of t equal to lambda power q f cap of lambda minus lambda power q minus 1 into f of 0. Here, lambda power q is Laplace transform of 1 by gamma of n minus q, and f cap of lambda is the Laplace transform of the function f of s. So the Laplace transform is lambda power q f cap of lambda minus lambda power q minus 1 into f cap of 0. Suppose if we choose higher order, that is alpha belongs to like 1, 2. So the derivative will be degrees, that is lambda power q f cap of lambda minus lambda power q minus f of 0 minus lambda power q minus 2 f dash of 0. Here we choose the second order differential equation, higher order differential equation. So we have one more initial conditions. So it will become lambda power q f cap of lambda minus lambda power q minus 1 f of 0 for this system, for this derivative. Now, the definition for Mittag-Leffler function. The two parameter Mittag-Leffler function is given by e q comma p of z, which is equal to summation k equal to 0 to infinity z power k divided by gamma of aq plus p for q comma p greater than 0, where q comma p is the fractional order. The Mittag-Leffler function is the generalization of generalization of exponential function. Usually, for the first order differential equations, we express the solutions in terms of exponential function. For the second order differential equations, second order integer order differential, second order differential equations, we give the solution in terms of sine and cosine function. Here, Mittag-Leffler function is the generalization of exponential function, sine and cosine function, also hyperbolic function. The Laplace transform of the Mittag-Leffler function is integral 0 to infinity e power minus st t power p minus 1 e q comma p plus or minus a t power q dt, which is equal to s power q minus p divided by s power q minus plus a. Here, I choose a is a scalar. Also, we can find the Mittag-Leffler function for n by n matrix. Also we can write. Also we can give the solution for n by n matrix in terms of Mittag-Leffler function. If we express the series EQ comma P of Z equal to summation k equal to 0 to infinity Z power k divided by gamma of k comma q, we can get a different kind of function. So the Laplace I will give the particular case for each one, that is P equal to 1, Q equal to 1, P equal to 2, Q equal to 2. I will give the particular case for P is an integer order. Now I give the Laplace transform for Mittag-Leffler function is T power P minus 1 E Q comma P plus or minus A T power Q of S, which is equal to S power Q minus P divided by S power Q minus plus A, which is the Laplace transform for Mittag-Leffler function. Here, the Mittag-Leffler function and the Laplace transform of Mittag-Leffler function is an important tool to write the solution for fractional differential equations. Now, these are all the particular cases. Suppose we choose P equal to 1. Q is any fractional number, but P equal to 1. P is an integer number. P equal to 1 is an integer. We get we represent E Q comma Z, which is equal to, where Z is the scalar, Q is the fractional number. Summation k equal to 0 to infinity Z power k divided by gamma of k Q plus 1. Suppose we choose P equal to Q equal to 1. We get exponential function. Just we substitute Q equal to 1, we get summation k equal to 0 to infinity Z power k divided by gamma of k plus 1 only. So we substitute k equal to 0, 1, 2, 3, and so on up to infinity, we get the exponential function. So the particular case of P equal to Q equal to 1 is exponential function. Suppose P equal to 1, Q equal to 2, we get e power Z minus 1 divided by Z. That is E 1 comma 2, which is equal to summation k equal to 0 to infinity Z power k divided by gamma of k plus 2. Just we express k equal to 0, 1, 2, 3 up to infinity, we get e power Z minus 1 divided by Z. Also, if we choose Q equal to 2 and P equal to 1, we get hyperbolic function. If we choose Q equal to P equal to 2, we get sin h of Z divided by Z. Hence, the Mittag-Leffler function is the generalization of exponential function, trigonometric function, hyperbolic function, etc. These are all the graphical representation for fractional derivative of the sine function, which range also lies between 0 to 1. For the fractional order alpha equal to 0.2, the fractional derivative of sine function where the derivative is 0.2, we get this. I give separate color for a different order, so one can find the behavior of fractional derivative for different order, that is alpha equal to 0.2, 0.4, 0.6, and 0.8, and alpha equal to 1. So the ranges lies between 0 to 1, which is the graphical representation for the fractional derivative of the sine function for a different order. Now we consider the linear fractional differential equations of order Q lies between open interval 0 to 1. That is d power c q, where c is the Caputo derivative, p is the fractional order, into x of t, which is equal to a x of t plus f of t, where t lies between the finite interval, closed interval 0 to t, with the initial condition x of 0 is equal to x naught. Now we find the solution for this equations. We know that Mittag-Leffler function, and also we know that the Laplace transform of Mittag-Leffler function. Also we know that Laplace transform of Caputo derivative. The Laplace transform of Caputo derivative is s power q x of s minus s power q minus 1 x of 0. Already I given in the previous slide. Lambda power q x of s minus lambda power q minus 1 into x of 0 or f of 0, whether the function is f or x. Here we choose x of t. So the Laplace transform of the capital derivative is x power q into x of s minus s power q minus 1 x of 0, where x of 0 is the initial function, which is equal to a. A is an n cross n matrix into x of s, where x of s is the Laplace transform of small x of t, f cap of s. F cap of s is the Laplace transform of f of t, the function f of t, and x of t is a state vector which belongs to R power n. F of t is the continuous function. A is an n cross n matrix. Now we apply the inverse Laplace transform laterally. Before we that, we take x of s as a one side, so we get s power q minus a into x of s minus x of s. We take minus s power q minus 1 x of 0 to this side, so we get right hand side, we get s power q minus 1 x of 0 plus f cap of s. So left hand side we have s power q minus a. Here s power q minus is the scalar, but a is a matrix, so we product s power q by identity matrix I. Therefore we get I into s power q or q power s power q into I minus a x cap of s is equal to s power q minus 1 x of 0. X of 0 is the initial conditions. Here initial condition is x naught. So we have x naught, s power q minus 1 into x naught plus f cap of s. Now we take s power q I minus a to left hand side. I'm sorry, right hand side. So we get x of s, which is equal to s power q minus 1 divided by s power q I minus a into x naught plus f cap f of s, capital F of s, divided by s power q I minus a. Now we apply the inverse Laplace transform function. That is, already we have Laplace transform. That is capital X cap of s. Capital X cap of s is the Laplace transform of small x of t. If we take inverse Laplace transform, the inverse Laplace transform and Laplace transform will be cancelled. We get only x of t. So we apply the inverse Laplace transform, L inverse of x of s, which is equal to L inverse of s power q minus 1 into s power q into I minus a power inverse x naught plus L inverse of f cap of s. Here the product is convolution product, because product of two functions. S power q I minus a is the one function and f cap of s is the other function. So we take the convolution. We take the convolution. So L inverse of f cap of capital F of s into L inverse of s power q I minus a inverse. So now we substitute the inverse Laplace transform of Mittag-Leffler function. We know that already. We know that the Laplace transform of Mittag-Leffler function is t power p minus 1 e q comma p plus or minus a t power q s. We take L to this side, that is right hand side. We get t power p minus 1 e q comma p a t power q, which is equal to L inverse of s power q minus p divided by s power q divided by a. We have in this form. So we apply the inverse Laplace transform of Mittag-Leffler function. We attain the solution of the system 3, that is x of t equal to e q of e q into a t power q x naught plus 0 to t minus s power q minus 1 e q q a t power a into t minus s power q f of s ds. Here eq denote the one parameter Mittag-Leffler function, eq comma q denote the two parameter Mittag-Leffler function. That is e q comma another q is 1. So simply we denote eq. That is one parameter Mittag-Leffler function. So this is the way to find solution for fractional differential. This is the one way to find solution for fractional differential equations by using Mittag-Leffler function. Just we apply the Laplace transform of Kaplan fractional derivative and apply the Laplace transform for Mittag-Leffler function. So so one can obtain the solution easily by using Laplace transform method. So which is the solution for system 3. Now we consider the integer order linear delay system. Here delay is constant. Now we enter into the perturbation of delay differential equations. Now we consider the integer order linear delay system with constant delay. That is, tau is constant. Tau is positive constant. X dash of t equal to ax of t plus b into x of t minus tau with the initial function x of t equal to psi of t, where t belongs to closed interval minus tau comma 0, which is called equation number 4. Here we define the first one is x dash of t, which is equal to x of t plus b into x of t minus tau, where t greater than or equal to 0. The initial function x of t equal to psi of t when t belongs to closed interval minus tau comma 0, where a comma b belongs to r power n cross n, that is n by n matrix with permutation with permutable ab equal to ba. The solution the state vector x of t belongs to r power n. The initial function psi of t from minus closed interval minus tau comma 0 to r power n is continuously differentiable function. Now we find the solution for system 4 in terms of exponential function, which is more complicated to write the solution because x of t, a into x of t plus b into x of t minus tau, both are state vector. So it is a little bit difficult to write the solution in terms of exponential function. So in the following slides, the following presentation, we will see about how to find the solution for this kind of system. Firstly, if we consider only linear system and write the solution for linear system without delay, we can easily give the solution for system 4 in the similar way. That is, if we consider x dash of t equal to ax of t with the initial function x of 0 equal to x naught. The equation number 5 is the corresponding linear system without a delay. That is, which is the corresponding linear system without a delay. X dash of t equal to ax of t with the initial function x of 0 is equal to x naught. This is called equation number 5, which has the solution x of t equal to e power at into x naught. So obviously we can prove, we can write the solution for system 5 with x of t equal to e power at x naught. Here e power at is the exponential of matrix A in the following form, that is e power at equal to I plus a into t by 1 factorial plus a squared into t squared divided by 2 factorial plus and so on, a power n into t power n divided by n factorial and so on. Here I is an identity matrix, A in n by n matrix. Here A is an n by n matrix. Now we give we give the solution for this kind of system. Now I wish to write the solution for system 4 in the similar way of system 5. That is, I will write the solution for system 4 in terms of matrix exponential with the matrix's perturbation. For this system 5, we prove the solution x of t equal to e power at, where e power at is we give the expression, that is I plus a into t by 1 factorial plus a squared into t squared divided by 2 factorial plus and so on, like this. In the similar way, we give the matrix expansion for perturbation, that is permutable matrices. So before we prove the solution for system 4, we remember some basic results. That is, for the matrix exponential e power at, have the formula e power a into t minus tau, which is equal to e power at into e power minus a tau. if you have any notes, you can just write it. I give detailed notes how to prove e power a into t minus tau, which is equal to e power a t into e power minus a tau. So we know that first we decompose the matrix e power a t onto Taylor series in neighborhood of t naught, where t naught equal to tau. For this matrix e power a t onto Taylor series in neighborhood of t naught. Now I choose t naught equal to this tau. So we obtain e power a t, which is equal to e power a tau plus a into e power a tau t minus tau divided by 1 factorial. So now I am just giving the expansion for the matrix e power a t in terms of Taylor series. Taylor series with onto Taylor series in neighborhood t naught. So I give e power a t equal to e power a tau plus a into e power a tau t minus tau divided by 1 factorial plus a squared e power a tau t minus tau whole square divided by 2 factorial plus and so on a power n e power a tau into t minus tau whole power n divided by n factorial plus and so on. Just I write the expansion of the matrix e power a t in terms of Taylor series in neighborhood t naught. So we take e power a tau as a common term. So we get I plus identity matrix I plus a into t minus tau divided by 1 factorial plus a squared t minus tau whole square divided by 2 factorial plus and so on a power n t minus tau whole power n divided by n factorial. E power a tau as is a common term. So we just put a square bracket. We have all the other expansion except e power a2 in this bracket. We have e power a2 as a common term. Now this square bracket can be written as in terms of e power a into t minus tau. I just repeat the square bracket term only. I plus a into t minus tau divided by 1 factorial plus a squared into t minus tau divided by 2 factorial plus a cube t minus tau whole cube divided by 3 factorial plus and so on a power n into t minus tau whole power n divided by n factorial. This series can be written in terms of e power a into t minus tau. Therefore, finally we have e power a t which is equal to e power a into t minus tau into a power t. So we take e power a t to left hand side. We have e power a t into e power minus a tau, because we take plus e power a tau to left side. So we have e power a t into e power minus a tau, which is equal to e power a into t minus tau. So which is the proof for the first result. E power a into t minus tau, which is equal to e power a t into e power minus a tau. So this is the simple proof. We just give this proof into Taylor series in neighborhood t naught equal to tau. Just we consider t naught equal to tau. We can easily find this result. Suppose here we have A is n by n matrix, but we find the solution for our system A and B are permutable matrix. So we give the expression with A and B are permutable matrix. Suppose we consider A and B are permutation matrices. That is, A and B are satisfying AB equal to BA. Then we prove that e power AT into B, which is equal to B into e power AT. E power AT into B, which is equal to B into e power AT. Because we prove, we give the solution in the following form. Now, already we know that e power AT, only matrix exponential function, that is I plus a into d by 1 factorial plus a squared into t squared divided by 2 factorial plus and so on a power n into t power n divided by n factorial plus and so on. Now we have e power at into b. So we have just we product with this expansion. Already we know that the expansion of e power a tau. We just product with B, we get B into BA D by 1 factorial plus B into A squared into T squared divided by 2 factorial plus and so on. B into A power n T power n divided by n factorial plus and so on. Now we take B as a common term. Remaining we get in the square bracket I plus A into T by 1 factorial plus A squared into T squared divided by 2 factorial plus and so on. A power n into T power n divided by n factorial plus and so on. So this expression we can be written in the form of B into e power a tau. Therefore, the matrix the perturbation matrices. Suppose if we consider A and B are perturbation matrices, we have the result e power at into B, which is equal to B into a power at by using in the similar way of result number 1. Now we consider delayed exponential of matrix B is a matrix function e power tau Bt that has the following form, that is e tau B power T, which is equal to 0 matrix, where T lies between open interval minus infinity to tau. We consider the system T less than or equal to 0, T greater than or equal to 0 with the initial function x of t equal to psi of t, where t belongs to open interval minus tau comma 0. So before minus tau, the exponential matrix is 0 matrix, that is theta, capital theta, and e power e tau b power t, which is equal to identity function, where t lies between minus tau less than or equal to t less than 0, and I plus b in b t by 1 factorial plus b squared t minus tau whole square divided by 2 factorial plus and so on, b power k t minus k minus 1 tau power k by k factorial, k where t lies between k minus 1 into tau less than or equal to t less than or equal to k tau, which is called delayed exponential matrix. Delayed exponential matrix. That is, we define the matrix for each interval. For each interval. So next we have the derivative for the exponential matrix D. Differentiating rule. That is d divided by dt into e tau power bt, which is equal to b into e tau b into t minus tau. That is the differentiation of the delayed exponential matrix is b into e tau b t minus 1, b t minus tau. Now also which is also a simple proof like result number 1. So there is a for result number 2 we have t divided by t e power bt tau, which is equal to d by dt. We know that e power bt tau, that is I plus the matrix expansion of e tau bt for the interval k minus 1 tau less than or equal to t strictly less than k, which is also given in the third term of the definition, delayed exponential matrix. Just we see the third term, I plus b into d by 1 factorial squared into t minus tau whole square divided by 2 factorial plus and so on. So we have the expansion, this I plus b into d by 1 factorial plus p squared into t minus tau whole square divided by 2 factorial plus and so on, b power k t minus k minus 1 into tau whole power k divided by k factorial. Now differentiating this expansion with respect to t. So we get the first term will become 0 because it is identity matrix. The second term keep b as a constant. So differentiating t divided by 1 factorial. So we get 1 divided by 1 factorial. Differentiating t with respect to t, we get 1. So b into 1 by 1 factorial. So remaining we get only b plus. Now we differentiate the second term. Keep b squared as a constant and differentiating t minus tau whole squared divided by 2 factorial with respect to t with respect to t. So we get b squared 2 into t minus tau whole power 1 divided by 2. So we get the numerator 2 and the denominator 2 will be cancelled. So we get b into t minus tau only. So the third term, b cube, keep as a constant. So now we differentiating t minus tau whole cube divided by 3 factorial with respect to t. So we just differentiate t minus tau whole cube. So we get 3 into t minus tau whole square divided by 3 factorial. 3 factorial can be written as 3 into 2 into 1. So the numerator 3 and the denominator 3 will be cancelled. So remaining we get 2 cross 1, that is 2. So we get b cube into t minus tau whole square divided by 2 plus and so on. We differentiating in this way. Finally, we get b power k t minus k minus 1 into tau whole power k minus 1 divided by k minus 1 factorial, because the k factorial can be written as k into k minus 1 into k minus 2, k minus 3 and so on into up to 1. So k numerator k, denominator k will be cancelled. Remaining we get k minus 1, k minus 2 in the following series. So it can be written as k minus 1 factorial. Now we take b as a common term. If we take a b as a common term, remaining we get in the square bracket I plus b into t minus tau divided by 1 factorial plus b squared into t minus tau whole square divided by 2 factorial plus and so on. B power k minus 1 t minus k minus 1 into tau whole power k minus 1 divided by k minus 1 factorial. So this bracket, the series of the series in the particular bracket can be written as e tau e suffix tau power b into t minus tau. Therefore we get b into e power b into t minus tau divided by tau. That is the derivative of the exponential delayed exponential matrix e power tau whole power b is b into e power b t minus tau divided by tau. This is also a simple proof. This is the rule of integration in the similar way of differentiation. That is the integration of delayed exponential matrix e tau bs is I into 1 by I into t by 1 factorial plus b into t square divided by, just differentiate with integrate with respect to t. So the first term will become t by 1 factorial, the second term will become t square divided by 2 factorial plus and so on. B power k into t minus k minus 1 into tau power k plus 1 divided by k plus 1 factorial. By using the above mentioned result, and represent the solution for system 4 with A and B are permutable matrix. Now, then the matrix x naught of t, capital X naught of t equal to e power a t e tau b1 t, where b1 equal to e power minus a tau into b. Our main aim is to write the solution for system 4 in terms of exponential function. Just we study what is the exponential matrix, what is the expansion of delayed exponential matrix for each interval, and its differentiating rule and its integrating rule with A and B are permutable. Now we take the matrix x naught of t equal to e power a t into e tau b1 of t, where b1 equal to e power minus a tau into b. For t less than or equal to 0 is the solution of the system 4, satisfying the initial condition x naught of t equal to e power a t, where t belongs to closed interval minus tau comma 0. So the equation number 6 is nothing but the solution of system 4. We just transform into exponential form. Also, we transform the initial condition x of t equal to psi of t, where t lies between closed interval minus tau comma 0, as x naught of t equal to e power a t, where t lies between minus tau comma 0. The matrix x naught of t is already defined in equation satisfying equation number 5. Equation number 5 is initial conditions. That is evident from the definition of exponential e power a t into e power tau b1 t. Let us show that on t less than or equal to 0, The matrix x naught of t is a solution of system 4 having a differentiated 6 we obtain. Just we differentiate equation number 6 we will obtain. We just differentiate the right side d by dt e power at into e tau b1 of t is equal to, first we differentiate e power at and keep e tau b1 of t as a constant, so we get a into e power at into e tau b1 of t. Now we keep e power at as a constant. Now we differentiate e tau b1 of t with respect to t, so we get b1 into e tau b1 t minus tau. So a into e power at e tau b1 of t plus e power at. We know that b1 equal to, already we know that b1 equal to e power minus a tau into b. So we substitute b1 equal to e power minus a tau into b into e tau b1 t minus tau. Therefore we get a into e power at into e power tau b1 t plus b into we write e power at into e power minus a tau as e power a into t minus tau into e tau b1 into t minus tau. So which is the differentiating rule. From equation number 6, one can write the left hand side d by dt d by dt x naught of t equal to a into x naught of t plus b into x of t minus tau. So we just write equation number 6 in terms of differential in the differential form. Now we prove the main results, the main solution by using the following theorem. That is, the theorem says that let the matrix A and B of the system 4 are permutable. That is, the system 4 x plus of t equal to A into x of t plus B into x of t minus tau with initial conditions x of t which is equal to psi of t, where t belongs to closed interval minus tau comma 0. Now we express the solution as x of t equal to e power a t plus tau into e tau b1 of t psi of minus tau plus integral minus tau to 0 e power a into t minus tau e tau b1 into t minus tau psi dash of s minus a into psi of s ds, which is the actual solution of the system 4. Now we found how we derive this solution. So the solution of the system 4 satisfying the initial condition x of t equal to psi of t, where t belongs to minus tau comma 0. One search in the following form. We have first we consider in the following form x of t equal to x naught into c plus integral minus tau to 0 x naught into t minus tau minus s y of s into ds. C is a vector of unknown constant. Y of t is a unknown continuously differentiable function. The matrix x naught is already defined in 7, which is x naught of t equal to e power a t, where t belongs to closed interval minus tau comma 0. Now we find each term. Let us choose c and y of t in such a way that they satisfy the initial conditions x of t equal to psi of t, t belongs to minus tau comma 0, are having x naught of t plus c plus minus tau to 0 x naught of t minus tau minus s y of s is ds, which is equal to psi of t. Now substitute or assume t equal to minus tau as it follows from 7, equation number 7. What is equation number 7? X naught of t, you know that capital X naught of t equal to e power a tau, we know that 7. X naught of t equal to e power a tau, which is initial function. Now we choose t equal to minus tau. We can choose whenever we choose t equal to minus tau, so we can take only this interval because t lies between closed interval minus tau comma 0. But we cannot choose in the previous equation 6 because in the previous equations t greater than or equal to 0. Now we choose, for that we choose t equal to minus tau. It follows equation number 7. So we substitute t equal to minus tau, we get x naught of minus tau equal to e power minus tau. So we take x naught of t minus, we substitute t equal to minus tau. So x naught of tau minus s, that is x naught of minus 2 tau minus s, which is equal to 0 matrix, where t lies between open interval minus tau comma 0. When x naught of minus 2 tau minus s is equal to e power minus a tau, when s is equal to tau. Just we substitute s is equal to tau, we get x naught of t minus tau minus s. So minus tau plus tau will be cancelled. We get x naught of t. Already we know that x naught of t, which is equal to e power minus a tau. For t belongs to closed interval minus tau comma 0. So thus we choose psi of minus tau equal to e power minus a tau into c. Obviously we can get c equal to, we take e power minus a to left side, we take c equal to e power a tau into psi of minus tau. And equation number 6 takes as a form x of t equal to e power a into t plus tau into e tau b1 into t psi of minus tau plus minus tau to 0 e power a into t minus tau into e tau b1 of t minus tau minus is y of s ds. So which is just the x of t. Now we found what is y of s. Since minus tau less than or equal to t less than or equal to 0, what to divide the interval on 2. The first interval is minus tau less than or equal to s less than or equal to t. So minus tau less than or equal to minus tau minus s less than or equal to t, and the matrix delayed exponential is equal to e tau b1 into t minus tau minus s, which is equal to identity, where minus tau less than or equal to s less than or equal to t. The second interval is less than or t less than or equal to s less than or equal to 0. So t minus tau less than or equal to t minus tau minus s less than or equal to minus tau, and the matrix delayed exponential is equal to e suffix tau b1 into t minus tau minus s, which is equal to 0 matrix whenever s lies between 0 less than or equal to s less than or equal to t, and e power minus at where s is equal to tau. Thus on the interval minus tau less than or equal to t less than or equal to 0, one can obtain e power a into t plus tau psi of minus tau plus integral minus tau to t e power minus a into t minus tau minus s y of s ds, which is psi of t. So which is called x of t. We know that x of t equals psi of t when t lies between closed interval minus tau comma 0. And having the just to differentiate the above equation, that is we differentiate equation number 9, we get a into e power a into t plus tau psi of minus tau. We know that the derivative of e power a into t plus tau is a into e power a into t plus tau into psi of minus tau. So we get a into e power a t plus tau psi of minus tau plus a into minus tau to 0 e power a into t minus tau minus s y of s ds plus e power minus a tau psi dash of t, where psi dash of t is the derivative of psi of t with respect to t. Solving equation number 9 and 10, we get a into psi of t e power minus a tau y of t equals psi dash of t. Just we take a into a into e power minus a tau to right hand side, we get y of t, which is equal to e power a tau psi dash of t minus a into psi of t. Just we substitute this y of t in equation number 9. We get the solution x of t equal to e power a into t plus tau e tau b1 into t psi of minus tau plus minus tau to 0 e power a into t minus tau e tau b1 into t minus tau minus is psi dash of s minus a into psi of s ds. So which is the solution of the system 4.
Excuse me, sir.
Now I wish to give sir.
Excuse me, sir. 1 second.
Yes, sir.
In the chat box, there is a participant named Vanaja, and she is sharing some another YouTube channel link to get the feedback link. Please do not subscribe that. And if you have subscribed it, please subscribe it. And we will share, the host will share the feedback link at the end of the session, and the feedback link will be posted in the YouTube channel, official AV80 channel. Okay, participants, please do not subscribe that. And Madam Vanaja, please do not post such kind of things in this sessions. Sir, please take over the session. Thank you.
Yeah, and now I wish to give the remark. Suppose if the matrix is zero matrix, then we get the solution x of t equal to e tau b t psi of minus tau plus minus tau to 0 e power e tau b into t minus tau minus s into psi dash of s. We know that A is a zero matrix. In substitute A, suppose we take A as a zero matrix in equation number 4. We just go to equation number 4. Yeah, this is the equation number 4. Suppose if we consider A is a zero matrix, then obviously the linear system will be reduced to x dash of t equal to d into x of t minus tau with the initial condition x of t equal to psi of t, where t belongs to minus tau comma 0. For this system, we have the solution. The A is a zero matrix, so it will become e power 0. E power 0 is 1. So remaining we get e power tau, e suffix tau, b1 into t psi of minus tau. Plus minus tau to 0. Also, it will become 1. E power 0, it will become 1. We get e tau b1 t minus tau minus s into psi dash of s. This term will become 0 because A is a zero matrix. So the solution, if we consider A is a zero matrix in equation number 4, we get the solution x of t equal to e tau bt psi of minus tau plus minus tau to 0 e tau b into t minus tau minus s psi dash of s into ds. So this is the particular case. So which is the solution of the system 4, and already we give the expansion of the delayed exponential matrix. So which is the solution for the linear delay differential equations where the delay is constant. By using the same approaches and the same methodology, we can write the solution for the corresponding fractional differential equations of equation number 4. That is, we have in equation number 4 x dash of t equal to a into x of t plus b into x of t minus tau. The corresponding fractional differential equation is d power cq or alpha, where c is the Caputo derivative, alpha is the fractional order, x of t, which is equal to a into x of t plus b into x of t minus tau, with the initial condition x of t equal to psi of t, where t belongs to minus tau comma 0, with a and b are permutable matrices, that is ab equal to ba. Now we find we apply the same methodology for fractional case. Now we consider equation number 11. The equation number 11 is Caputo fractional differential equation of or fractional differential equation of equation number 4. That is d power c into alpha x of t equal to a into x of t plus b into x of t minus tau, where t lies between 0 less than or equal to t minus, and sorry, t is greater than or equal to 0 with the x of t equal to psi of t, where t belongs to minus tau comma 0, where d power c alpha denote the Caputo fractional derivative, where alpha lies between open interval 0 to 1. A and B belongs to R power n cross n, that is n by n matrix, constant matrix, also permutable. The state vector x of t belongs to R power n. The initial function psi of t from minus tau comma 0 to R power n is a arbitrary continuously differentiable function. Now the definition, one is called delayed Mittag-Leffler matrix function. Already we know that the Mittag-Leffler function, that is e q comma p, which is u p comma q of a into t power q, which is equal to summation k equal to 0 to infinity a power k divided by gamma of qk plus p. Now we write the Mittag-Leffler function for delay delay parameter. That is, we define the Mittag-Leffler function for each interval. That is minus tau less than t less than or equal to 0. The delayed Mittag-Leffler function will become 0 matrix, and minus tau less than t less than or equal to 0. The delayed Mittag-Leffler function is I into t plus tau power beta minus 1 divided by gamma of beta plus and so on up to I into t plus tau power beta minus 1 divided by gamma of beta plus beta into t power alpha plus beta minus 1 divided by alpha plus beta plus and so on beta power k into t minus k minus 1 into tau power k alpha plus beta minus 1 divided by gamma of k alpha plus beta, where t lies between open interval k minus 1 into tau less than t less than or equal to k tau, called delayed Mittag-Leffler matrix function, like exponential function. In definition 1, just B as a constant matrix. There is no permutable. There is any other matrix like a permutable matrix. Only we have only one matrix B, and we express for delay parameter. Now we take delayed perturbation of two parameter Mittag-Leffler type matrix function x power b tau alpha beta of t generated by a comma b is defined by in the following expression. Here a and b are permutable, that is ab equal to ba. Therefore we define x power a comma b t alpha comma beta of t equal to 0 matrix, where t belongs to open interval minus tau comma closed interval minus tau comma open interval 0, and we get identity matrix when t equal to 0. We just substitute in the Mittag-Leffler function. We get this delay matrix. We substitute for each interval. For the interval k minus 1 into tau less than t less than or equal to k tau, we get the delayed perturbation of two parameter Mittag-Leffler function is summation I equal to 0 to infinity summation j equal to 0 to k minus 1 q I plus 1 into j tau t minus j tau power I alpha plus beta minus 1 divided by gamma of I alpha plus beta. Also, it has the differentiating rule and integrating rule, like integer order differentiation. Already we give the differentiation rule and the integration rule for exponential function. See result number 1 and 2 and 3. The integration rule and the differentiation rule for exponential function. In the similar way, we can find the differentiation and the integration rule for Mittag-Leffler function, because Mittag-Leffler function is the generalization of exponential function. So we have the following rule. If A is a 0 matrix, then it will be reduced to delayed exponential matrix. That is definition number 1. Suppose if we assume that in the delayed perturbation of Mittag-Leffler function, A as a 0 matrix, it will be reduced to delayed Mittag-Leffler matrix function. That is, we get e power b tau alpha comma beta t minus tau, where t minus tau lies between closed interval k minus 1 into tau comma k tau. Suppose if we consider b as a 0 matrix, we will get t power beta minus 1 e alpha comma beta t power a t power alpha. It just like Mittag-Leffler matrix function, ordinary Mittag-Leffler matrix function without any delay, because the delay term will become 0. So only we have A. A is a ordinary n by n matrix. So we get Mittag-Leffler matrix function. If we consider alpha equal to beta equal to 1, suppose if we choose alpha equal to beta equal to 1, obviously the system will reduce to integer order differential equation, like the system 4. So if we choose alpha equal to beta equal to 1 and the matrix are permutable, that is AB equal to BA, then the matrix is reduced to e power at e b1 into t minus tau. Already we know that b1 equal to p into e power minus a tau. b1 equal to e power minus a tau into b, or b into e power minus a tau. For the interval k minus 1 into tau strictly less than t minus tau less than or equal to k tau. So we have the same integration rule, that is the integration of the delayed Mittag-Leffler matrix function x power a comma b suffix t comma alpha r minus s into der. We have summation I equal to 0 to infinity, summation j equal to 0 to k minus 1 q I plus 1 into j tau t minus s minus a tau power I alpha gamma 1 minus alpha divided by gamma I alpha plus 1. The same integration rule. By using this integration rule and the differentiation rule, we have the following solution for system 11. We have the following solution for system 11. That is x of t equal to x power a comma b t tau comma alpha comma 1 t plus tau psi of minus tau plus integral minus tau to 0 x power a comma b suffix tau comma alpha t minus tau into coupled derivative of minus tau psi of s minus a into psi of s ds. Just we compare with the solution of system number 4 with the solution of system number 11. The solution of system number 11 is we express the solution in terms of delayed Mittag-Leffler matrix function, and we express the solution of system 4 in terms of delayed exponential matrix function. If we compare these two solutions, we can get the unique and the beauty of fractional differential equation. So this is the idea and methodology to find solution for linear delay differential equations with permutable matrix, whether the differential equation is integer order or fractional order. This is the way. This is the one way to find the solution. Now we move to the qualitative behavior of dynamical system, that is existence, observability, controllability, stability, and optimal control for the considered system 4 and 11. 4 is the integer order system, 11 is the corresponding fractional order system. Suppose if we consider the system 4 or 11 is said to be controllable on closed interval 0 comma b if for every x naught xb both are arbitrary, that is x naught is the initial state and the xb is the final state, belongs to R power n, there exists a control input via u of t belongs to R power n, such that the corresponding solution of the system 4 or 11 satisfies the initial condition x naught equal x of 0 equal to x naught and x of b equal to xb. Suppose if we consider delay differential equations in this system, we consider delay differential equations. Also, we need to check x of 0 is equal to x naught and x of t equal to psi of t. We need to check x of t equal to psi of t also, and x of b equal to xb. Suppose if the system is cannot be controllable, we can define different kind. We can define different kind of definition like null controllable, exact null controllable, approximately null controllable. We can define different kind of definitions. That is, the system 11 or 4 is said to be null controllable on the finite interval close to interval 0 comma b if for every continuous function x naught belongs to R power n, there exists a control input u of t belongs to R power m, such that the solution x of t of 2 satisfies x of 0 equal to x naught and x of b equal to 0. If we consider delay differential equations, it should be satisfies x of 0 is equal to x naught and x of t equal to psi of t, and the interval t belongs to closed interval minus tau comma 0. To prove this controllability results for finite for linear system, we can prove by using controllability Gramian matrix under rank correlation method. Suppose if we consider non-linear system, we prove to prove the system is controllable by using approximation method or fixed point approaches, any fixed point theorem like Banach contraction for existence and uniqueness of fixed point, Skadar fixed point, Skaffer fixed point, Larry Skadar fixed point, Kronosky fixed point. We can apply any one of the fixed point and we can prove the existence of fixed point, which point is the solution of the system x of t. We substitute x of 0 equal to x, we substitute x of 0 equal to x naught and x of b equal to xb. Obviously, the system is controllable on the interval close to interval 0 comma b. Already we know that the qualitative behavior of the controllability. That is, if it is possible to steer the dynamical system from arbitrary initials to arbitrary final state by using set of all admissible control. Now, these are all some methodology to prove the system 4 is controllable. The first methodology is by defining delayed Gramian matrix, delayed controllability Gramian matrix. The second methodology is rank correlation method by Taylor-Hamiltonian here. That is, the Gramian matrix is given f suffix tau over bf. Bf is the final time. So integral 0 to bf exponential of a into b minus s into exponential of b1 into bf minus tau minus s into c into c star exponential of a star into bf minus tau exponential of tau into b1 star bf minus tau minus s. Here star is the transpose of the matrix. C is the coefficient of control input. A is the coefficient of the first state ax of t, and b is the coefficient of b into x of t minus tau. That is, the system is x dash of t equal to a x of t plus b into x of t minus tau plus c into u of t. Because we study the controllability, so we need to include the introduce the control input. Also, one can prove by using rank correlation method. That is Sn equal to n. So these are all the graphical representation for the concept of controllability. Just we choose the initial state to 0, initial state to 1 to 0, and the initial state 2 to 0. Obviously, the system is null controllable because we know that the definition of null controllability: x of x naught equal to x naught and x of b, that is final time, equal to 0. It will transfer to origin. Therefore, this is the graphical representation for the system is null controllable. This is the another graphical representation for the system is null controllable. That is, initial state is 0.5 to 0, another state 1.5 to 0, and the interval closed interval 0,2. This is the definition for the system is controllable. That is, the initial state is 0 to 1 and 1 to 0. The initial states are 0 and 1. The final states are 1 and 0. The another figure is graphical trajectory of the control parameter. This is the another graphical representation for the concept of controllability. The initial states are 1 and 2. The final states are 2 and 1. That is 1 to 2, 2 to 1. Now, in the category of another qualitative behavior is stability. Consider the following linear time invariant system: d power c into alpha x of t equal to ax of t, where alpha lies between open interval 0 to 1. With the we choose t belongs to closed interval t0 to t1. That is, initial time is t0, final time is t1. With the initial condition x of t0 equal to x0, we have the solutions by using the Mittag-Leffler function. Already we know that by applying inverse Laplace transform and Laplace transform of Caputo fractional derivative and Mittag-Leffler function, one can write the solution for the system 12 as x of t equal to e alpha into a of t minus t0 over alpha into x. So first we need to prove the system is stable, and we can prove that the system is asymptotically stable. That is, the solution is said to be asymptotically stable if, in addition to be stable, that is, x of t tends to 0 as t tends to infinity. The fractional dynamical system 12 is asymptotically stable if and only if modulus of the argument of spectrum of A is strictly greater than alpha pi divided by 2. The spectrum of A tends to the spectrum of A is the sum of all eigenvalues. So if we satisfy these conditions, this system 12 is asymptotically stable. So this is the another qualitative behavior of the dynamical system. So these are all the following important reference to study fractional calculus and qualitative behavior of fractional delay differential equations with permutable matrix. So I put some selective reference for these studies. One can refer many books, monograph, and research article available in internet. So one can refer. So number 6 also very important. for existence of wild solution for infinity case, one can study reference number 10. So these are all the following. These are all the important reference and reference books and article. So thank you, Ananda. If you have any questions, your questions are welcome.
Thank you, sir. Thank you for your insightful presentation. Participants, in case of any queries, please raise your hand, or you can enter your queries in the Q&A chat box.
Participants, the feedback link for this webinar is posted in the chat box. Kindly make use of it.
Srinivasan sir, I can see you have raised your hands. Please unmute yourself. Chaitanya ma'am, in case of question, please unmute yourself. Or else you can, chat your queries. Okay.
Okay, if you have any doubt or questions, also one can contact me through my via my email ID. That is my email ID satiraj133@gmail.com. If you need any material, any book or any book or research article regarding this presentations, you can contact me via this email.
Anandan sir, can we move on to the vote of thanks?
Yeah, madam. Are you audible?
Yes, sir. Yes, sir. Yes, sir. You're audible. Okay. So we'll move on to the vote of thanks. Now I request Dr. V. Anandan, HOD of Department of Max, to propose the vote of thanks.
Yes, ma'am. Thank you, ma'am. First, my sincere thanks to Dr. Satyaraj. You gave a valuable, wonderful section. It's really very useful for us to. And second, I have to thanks to all the participation to attend the second day of International FDP. Once again, I thanks to all. Thank you, sir.
Yes, thank you, sir. I also express my honor thanks to the Chief Partner, Dr. S. Shanmugavalli Madam, Director, School of Arts and Science, AV Campus, and I thank for giving me the opportunity. Also, I thank the coordinator, Dr. V. Anandan sir, Head of the Department of Mathematics, AV Campus. And I thank the organizing team members, Mr. S. Loganathan sir, Mr. M. Ramesh sir for their wonderful organization. Also, I thank all the participants. I hope this session will be useful to those who are studying and doing research in the basic in the fractional differential equations. If you have any doubt, any queries, you are welcome to contact me via my email address satiraj133@gmail.com. Thank you, Ananda.
Thank you, thank you. Sam, sir.
Anand sir, shall we close the session, sir?
Yeah, you have post the feedback link, sir.
Yes, sir. Yes, sir.
Yeah, okay, sir. Okay, thank you. Yeah, shall we wind up, sir?
Sam will wait for 5 minutes. Let them fill the feedback form.
Okay, sir. Welcome, sir.
Okay.
No problem.
5 minutes, sir.
Okay, sure.
Okay.